So this chapter trying to start to look into more detail about the motor parameter through the equivalent circuitry, and then we are able to start to control the motor. We start to learn how to control the motor, but not yet. Let's go through the motor parameter first. So in here, we're going to learn how to do the measurement. You see in the transformer, we have the open circuit test and closed circuit test. In the induction motor, we also have something similar, but we call it the lock rotor test or block rotor test and also open circuit test. It's something similar to do that. We can able to use it to measure the parameter. So from the torque and speed characteristic, we are able to work out how the torque equation look like. In the DC motor, we have the torque equation, which is quite straightforward, very simple formulation. But however, for induction motor, that's more AC, the waveform and also the circuit are quite complicated, then the formulation also more complicated, but we're going to show you how it looks like. So firstly, we try to ask you, we have been using voltage to control the motor speed, but how about for AC motor? Are we going to do that? The question here will be, actually, the AC motor is sine wave. How are we going to using a single sine wave to control both the motor torque and motor speed? That's the two major parameters we need to control motor, right? So what do you think? Anybody can give me a hand? How to control using a sine wave, not DC, right? Can we do that? Using a DC is quite straightforward. We have the DC motor equation, but AC motor equation is quite something quite different. Do you think we can able to use a sine wave to operate only the voltage to control the motor speed and motor torque? Can we do that?
Yes, that you would regulate like the frequency, sine wave, right?
Yeah, you regulate the frequency of sine wave. That's a really good point. We usually keep the slip to be small to have a high performance of the motor. That is the stable region. In the stable region, if you do remember that, so this is the stable region. And the slip here, slip equal to 0, slip equal to 1. So this is the slip here. S is small here. So we always tend to operate the motor when the slip is small, just a few percent, less than 10%. So that's to say our synchronous frequency need to be always adjusted accordingly to the motor speed. If you want to run the motor high speed, you use higher synchronous frequency and vice versa. In this case, you always keep the motor in this stable region, then always keep the speed here close to S equal to 0. That means when it close to S equal to 0, that means the two frequencies are quite close to each other. So that's what we do. So that means when we control a sine wave, we need to also not only control the amplitude, also control the frequency of sine wave. So that means here we have 60 Hz. We can only run the motor at 3,600 RPM. But if the motor goes down to lower frequency, you can adjust the sine wave. You can't do that. Sine wave, how do you change the frequency? You can only change the voltage by using a potentiometer or resistor or transformer, right? Auto transform. But to change the frequency of sine wave is not so easy. You need to use power electronics to do that. So adjust using inverter, which we will discuss further how to use an inverter. But basically, you can see that only a sine wave to control both the speed and the torque, we have some difficulty, but we need to use additional method to do that. So that's why inverter is the item we can able to use to adjust the voltage and the frequency. So that's the way we control the induction motor. But at least that is not so simple. Even though we can adjust the voltage and the frequency, doesn't mean we can able to control the speed and the torque in directly. So we need to be careful about how we're able to do that. So can we use the DC applied to induction motor? Of course, the answer will be no, we cannot. Induction motor is AC motor. We are never to use a DC applied to them. We need to go through an inverter. The DC will firstly go through an inverter and then go to the motor. So that means the inverter usually means DC to AC converter. So we'll do that. So what kind of component will be in motor controller? So component in motor controller, of course, we mean the inverter. Inverter consists of a number of the power transistor to do the switching. So we haven't covered it here, but basically you can see that there will be at least 6 transistors to work with the three-phase voltage. And then the operating parameter, what is the operating parameter affect the torque performance? Later on we'll discuss that in more detail. So that is to say, we have to look into not only the voltage and also frequency, and also a lot of the control parameter. And the last question will be, do you think the torque and the motor current are correlated to each other like this motor? Any comment? We did that for DC motor, the torque is proportional to IA, the current. How about for induction motor? Do you think it's the same? So what do you think?
Yes.
Yes. The ratio may not be directly proportional to the current, but something proportional. Actually proportional to current squared. So that would be really interesting question we'd like to do. So the content of this chapter, we're looking into some method for the basic fundamental method for testing. So we got going to go through them, and we also discuss about the torque equation. The torque equation is going to examine about how we control the motor. And then we're also looking into the speed control. So the measurement of the induction motor is very similar to the measurement of the transformer. So you see a transformer, we have the equivalent circuitry, which we have the primary part and secondary part. We also magnetizing. So you can see that our induction motor equivalent circuitry are also quite similar. So in here, we can able to use the equivalent circuitry, which we can convert into torque equation. We can able to predict the performance, even though the efficiency we're able to do that. More importantly, will be how we control that. At the moment, we only talk about the open circuit operation. That means we don't control the feedback. We don't feedback the torque and we don't feedback the speed. But usually for control system, we tend to have a feedback control. Are you learning the control system now? I mean, control engineering semester? Okay, so that will be, so that's one of the problem will be so many things you have to learn. They all correlate to each other. But after you learn the control engineering, then in next year, we start to have apply the control into various systems. Like power electronics, we also need to learn how to control them. But anyway, so later on, we also show you the short circuit test is also called the log motor test, something we use together to measure or to examine about the motor parameter. And we also open circuit test that also quite similar to what we learned in the transformer. And then we can therefore using this similarity or analogy to understand how to test the motor. So the basic, because just now you also asked me the correlation between the transformer and induction motor. Here is a quick table to show you the correlation. So you see the primary winding, I always use the word primary, mean the stator part, and the secondary is the rotor part. They actually really look like transformer. It's just a rotating transformer. And we have also magnetic core. Magnetic core appear in both the rotor and stator too. And then we also have the load connect to the secondary circuitry, but now then the load will be mechanical connect to the shaft. So that's how we correlate them. But the difference is in the transformer, the secondary winding will be connect to the outside circuitry, become transform the voltage. But in the rotor part, for instance, for the squirrel cage will be short circuit in the secondary. We don't need to connect electrical current to the outside world. We only need to convert them into mechanical power. So that's slightly different between the two systems. Then firstly, we need to understand about the testing. So the open circuit test and also short circuit test is two really famous tests for induction motor. You have to learn it. So you understand what it is, then you can use it to correlate what you learn in the transformer. So in the transformer, then you can see that the second winding will open circuitry and primary excited at certain winding. We do the same thing in the induction motor. So how we go to open circuit? Because we have to not connect anything in the rotor winding. Open circuit, that means we do not connect any mechanical load to the rotor. Let the rotor to free rotate without any influence. So you can see that very similar to the open circuit. As just now we mentioned, the torque is proportional to the current anyway. The current means the secondary side current. So that is to say, if you do not connect anything to the secondary side to the rotor, then that means the rotor current can be equal to 0 or can be negligible. So in this case, more similar to open circuit test as in the transformer. So that's why we can use this method. We can therefore eliminate all the rotor current. We can therefore eliminate at the moment. So that we can, using the open circuit test to measure the magnetizing component. You can see that if you got using a T model here, right? So that's a rotor. That's the stator. Now then, this is being not connected to anything. So that means the current will disappear. So we only have this looping. So when we measure open circuit, when we apply voltage here, we can able to use the open circuit to estimate the magnetizing component, perhaps also the stator component too. And then we're able to estimate about the core losses. So that's how we get the open circuit test. The next is the short circuit test. Short circuit test, that means we try to short circuit the secondary. But of course, in here, the rotor already short circuit, right? But so our short circuit test is not really short circuit, but we put the block rotor test. We blocking the rotor, not allow the rotor to rotate. So obviously, you can see that in this case, we are trying to demand for high current for the rotor. Because when you're blocking the rotor try to use more current, create more torque to make it rotate, but it's not doing that. So that means in this case, we're able to have much higher current in the stator current and motor current. So that means more look like a short circuitry in the secondary side, in the rotor circuit side. So that, of course, strictly speaking, we use block motor because we are not short circuit the secondary side, we're only blocking. And some of the textbook, they also using the word called log motor. Log motor test also being used. So in this case, you can see that our circuitry will become like that. A T model also become that. And then we allow the circuitry to floating in here. Because we are using block motor, the current will be quite large. Then we usually using low voltage to energize in that motor so that it won't blow up, it won't become too high current. If too high voltage, you'll be using standard voltage like 200 volt or 100 something volt with high voltage. We usually use a portion voltage, maybe 10%, 20% of the voltage in order to excite on the motor primary side and then to measure current. So in this case, because we use much low voltage, the losses in the magnetizing here, this voltage will be much smaller. So we can actually ignore about the magnetizing component here. So the short circuit test or so-called the block motor test and actually become this loop. So the current will pass through the R1, X1 here and R2, X2 here. So in this case, you can estimate the combination of these four components. So that's how we're trying to do. So now then we go back to our equivalent circuitry. From this circuitry, we start to understand how we conduct the two major tests. So open circuit and short circuit test. So from this circuitry, of course, if we use the short circuit or block motor test, we have a huge current pass through in here. So that's how we're able to obtain that. So let's see for this circuitry, what we can modify about the circuitry. Firstly, we can just combine, for the measurement, we combine the two resistors together, which is R2 dash over S, become this. So other combine them, we only have two resistor and two inductor in the primary side and secondary side. Of course, we do have the magnetizing in the air gap. So next thing to do will be if some of the equivalent circuitry, we may not consider the core losses RC. Because as I mentioned before, core loss, you cannot measure it, you don't know where it is. But one way we can do will be, we just lump the RC into the vintage loss and frictional losses. Because how we calculate core losses, we use one different way to calculate all the losses is like the conductor losses and the motor output. The remaining part, this kind of power must be the core losses. So that means the core loss only estimate in such a way. So this kind of core loss, we may not able to differentiate it properly between the vintage or friction and also the magnetic core losses. So that's why somehow this resistor, RC, we can therefore lump it together with this component to make the circuit simple. And you can see that when we try to use the log motor test and open circuit test, we may not able to calculate the resistance because the resistance only a parallel component. It's not actually there. We just for modeling convenience, we put a resistor there. It actually does not exist. We just putting a resistor there to represent the losses. So that's another model we can use will be this one. And sometimes if the magnetizing inductance is quite large, that means its inductance can be negligible. In this case, we can really to remove that, become this simplified circuitry. Then when we conduct the short circuit test, we can just estimate the current pass through this four components. That should be good enough. So there's a many ways we can represent that. Of course, different representation have different kind of the pros and cons, which because we already eliminate some component. So let's see how we going to do the next part will be how we conduct the losses. But before that, because I know we are not quite familiar with the three-phase, so I put a few chapters here to show you some basic information of the three-phase system. Usually, the three-phase should be conducted by the EE65 or Engineering 65 in the last few chapters. But we have to show you first before you learn it. Okay. I'm not quite sure how they're going to show. So who's now teaching the EE65? Or Engineering 65?
Engineering, who's teaching engineering 65? We'll find out.
This semester for 65 is bachelor.
Anyway, so for the three-phase power, you see that we have three-phase. So if we only to measure a single phase, will be quite straightforward. But three-phase, we can consider three-phase as the phase voltage and line voltage because two items here. So if we got a three-phase in here, like this three-phase, then if we measure the power for this one, so for example, like PL1, PL2, and PL3, you see these three of them can be separately measured. So that's why I can consider the total power will be summation of three of them together. For three-phase, usually we prefer to be three-phase balanced, especially a single induction motor. We try to make it symmetrical, otherwise the torque will be unbalanced with bias to a certain angle. So in this case, we prefer to the three-phase balance for each of the line L1 line, L2, L3. They should be equal to each other. The summation of power should be equal. So now then, there's some famous method to measure the power. So that's a kind of classical method. You don't need to really consider so important. But in the old day, when we don't have sufficient equipment, we tend to use the two power method to measure them using two watt meter. So this two watt meter, we have only 2 meters to be able to measure total power. So there's a really classical method. So that's why since most of the textbook also include this method, I will show it to you. But of course nowadays when you can have some three-phase meter, you can just plug in the phase voltage and phase current, you can directly calculate voltage. Internally, they may use this method to do it. So this 2 watt-meter method will be as such. You see, when we have a motor, if you want to measure its power, then we can just measure its current and also the line voltage. The line voltage is the voltage between the two lines. So the motor can be connected in delta or star. But the motor itself can be a black dot. You don't need to care about what it is. But bear in mind, you can see that the line voltage will be the difference between two phases. For example, we have phase A, B, and C, and then the phase A voltage minus the phase B voltage is the VAB will be equal to multiplied by its current. I call it W1. That will be measured by one of the power meter. And then we also have another phase, which from C phase and the B phase, the different, and then I can also measure the other power. And then we found that the summation of these two, we're just adding these two together, and then some of them have common factor. Eventually, we can get the total power will equal to its phase voltage multiplied by its phase current. Phase voltage, phase voltage, and phase current for each of the A, B, C phase. So happen to be, we can able to use the 2 wattmeter method. We can able to measure the total power. But of course, using this method, we're not quite sure about the three-phase balance or not, or the power factor, what it is. But we do have a method to do that. So this is really typical classical method, how we measure the power for three-phase motor or three-phase system. So this is a basic formulation. You can use it to do that. Bear in mind that because you have three-phase, we don't need to connect the neutral. So that means the three-phase current for symmetrical motor system must be bounded and equal. So that's why the summation of free current is equal to 0. You can see that if a motor, we don't have the neutral, no neutral current. Of course, the three-phase current A, B, C must sum to 0, but because no current can go anywhere. So that's how we can see the characteristic for three-phase motor. So bear in mind, 2 wattmeter is one of the classical method. You may need to learn how to do that. And then we can also use the 2 meter to calculate the power factor. So the methods are quite standard because for three-phase meter, if they do have power factor, the W1 and W2 don't need to be equal exactly. So the difference between these two will give you the power factor. So which we can able to use it to get the power factor. But anyway, if the three-phase is balanced, then the summation is the total power, and divided by 3 will be power for each phase. In this case, we assume the three-phase are balanced. Of course, if you can also using 3 meter to measure the power for each of the phase, then that could be more accurate. So in here, I just show you a typical method. We can use the 2 wattmeter method to measure the power. So after we finish this power measurement, for instance, you got a induction motor, and then you can use many different methods to measure the power. But all the analysis here, we tend to use so-called the per phase analysis. A three-phase motor has 3 phases. How do we conduct the measurement? We just are using one of the phase to conduct the measurement to measure the phase voltage and phase current. From there, we put them into our equivalent circuit model to estimate all the parameters. So in here, firstly, we do the low-load test. That means so-called the open circuit test. Then the losses, we can able to determine about the losses, including friction, windage, and also the core losses. These are 3 major losses. When we input energy, subtract all the losses, become our output energy. And then we do have magnetizing component. The magnetizing component will be the inductor we mentioned just now. We also have the core loss component, which is the magnetic losses. So the way to do that, open circuit test, we run the motor at rated voltage and rated frequency. If the motor is 60 Hertz and 120 volt, we're just using that voltage frequency to excite the motor. Open circuit test means we do not connect any load, so that means we do not connect any mechanical load. In this case, the motor current should be equal to really small, maybe more look like negligible in the voltage side. But in the stator side, we do have the current. You can see that. So now is the more. So this current, I2, will be really, really small. So that's why when we measure this current, it look like we only connecting the magnetizing and also the stator side. In here, we got the R1, X1, we got the XM here. So when we measure, it just look like this few components connect in series. Then we are able to conduct the calculation of measurement about what they are. So we firstly measure the line voltage. Once we measure the line voltage, we can convert them into phase voltage, quite straightforward. And then we can measure the current, and then we can measure the power. Using power meter or any other meter, then you can measure the voltage, current, and the power. From there, you can, just like what we did for the transformer. And then we can also measure this data resistance by using multimeter, the ohmmeter, to measure it. So the question is, why can we estimate the stator resistance using this three measurement? Yes?
Power equals I squared R.
Yeah, power equal to I squared R for the resistive power loss. Yeah. So can we measure the R1 resistance from these three measurements? Can we? Yes? Not quite exactly, because when we measure the low power, what kind of power difference should be? That include quite a few items. Firstly, from the model we have here, then firstly, this power may include the stator resistance, and then we could also, if this loop here, what this loop will pass through, the inductance probably is not really the losses, even inductive losses is not the real power losses. But the other losses like in here could be the friction, vintage loss, and the core loss. So that means the low power P1 here could including the R1 losses plus other mechanical losses. So that's why we do not use this method only for the R1. R1 can measure using a ohmmeter, a multimeter to measure the resistance. And after this one subtract these losses, will be the summation of all the vintage losses and also the core losses. Right? So now then, that's how we did. So because we assume the motor is balanced, so we divide by √3, then we can get the per phase voltage. But that assumes to be star connected. If the motor is delta connected, then the √3 will put it in the current, not the voltage. Do you get that point? Yeah. So for the star connected, so if you measure this voltage, that's a line voltage, but the phase voltage is here. Phase voltage here, and difference between these two by the √3 relationship, right? I think you all remember that. We do have formulation for you. So now that you understand the basic formulation between the three phase, with how we use the √3. Yeah. For this Y-connected motor or star-connected motor, then the voltage is different by √3. And here. And the current, this current, I1 current is also same as the phase current. Phase current, because they are star-connected. Yeah. But of course, if a delta-connected motor, then we need to use another formulation. Yeah. So you do need to have clear mind between the star-connected motor and the delta-connected motor. Do you get that? You see, are you okay with that? So now then we got the current, and the power also divided by 3, because just now this we are using total power, but now we can divide by 3. So total power divided by 3. So the low impedance, the impedance. So when you try to estimate about this loop, then voltage divided by current give us the impedance, the whole impedance in here. So that impedance including all the metasync component, wheel component, and X1 component. And we also have the low resistance. So just now we say, oh, the resistance, we have some resistance, but wheel power divided by I squared. So that resistance, we are not quite sure what resistance it is, because that resistance is not equal to R1. It can be combination R1 plus core losses plus other frictional losses. So this kind of RNL is some resistance, but we are not quite sure what it related to. Okay? So that's why we have to use other method, measurement of R1 stator resistance for the calculation. So next, the low reaction. So now that you get this one, you have the total impedance here. And then if we minus the resistive part, then we end up with the X part. So the X part, of course, is all the inductive part here. So if the inductive part, we can see that that will relate to here. Yeah. So that mean X and L, if we subtract the X1 here, then we can therefore get the magnetizing. So that's a simplified method. We're able to estimate about the magnetizing component. And where the X1 come from, we're going to get it from the log volta test. So that's a typical method. We're going to do it. At that point, would there be any question? It's not confusing, but we just a number equation. But you see that equation are very similar to the transformer. It's very much form. If you familiar with transformer log volta test and the short circuit test, open circuit test, it will be quite similar. So again, we said this calculation, the real part of the resistance is not actually equal to the R1. It's not equal to the stator resistance, but because it may relate to a few components, because that losses relate to core loss, the vintage loss, and also the stator losses. So that's why, but the stator copper loss is just I square R. Then the core loss is from the stator magnetic core, and also friction and vintage loss with something we may not know, depend on the motor parameter. So if we can assume the vintage and frictional loss is small for the moment, then we can therefore calculate the core loss roughly by this simple formulation. The losses we have just now, because R1 we can measure it, because it measures the resistance for the stator resistance, then you can measure the copper losses, and the remaining part will be the core losses. So according to these core losses, we may have some component for the vintage loss, but at the moment we just ignore that first. Then we can able to estimate about the core loss. Then if you want to get the core loss resistance, you can just use this formulation to do that. V square over R, that you can get the core loss resistance. So that is the T model resistance here. I'll see. So that's how we can estimate this resistance. You see this kind of open circuit test and short circuit test never can make the exact measurement. Everything will be approximation. Even though in this approximation, we just assume the friction and vintage loss is negligible, then because actually we don't know. Rotating a motor, how do we know the friction and the vintage loss? Impossible. We just assume they are negligible, then we test the total losses minus the conductive loss in the copper winding, then this is the core loss. Then in the core loss, we therefore estimate the core loss resistance. So that's the basic method we can use. So this method has limitation, but we are all doing it. All right. Any question up to this platform? So next is the log rotor test or the block rotor test. So when we blocking the rotor, not allow the rotor to rotate, then we also tend to use lower voltage applied to the motor. Then in this case, the voltage appear on the magnetizing will be quite small, so we can ignore all the magnetizing losses. Even the core loss will be lower because the core loss are depend on the B field. If a low voltage, the magnetic field in the magnetizing will be small anyway. So that's mean in here we can ignore the core losses and magnetizing. So we assume all the losses will go to the motor winding and also the X1 and X2. So now then we can use this method to estimate the leak gauge component. So that means the component here, so become like that. So this magnetizing can just ignore it for a moment because the voltage here, the voltage will be really low voltage, be much low voltage. When we have low voltage, this voltage also small, so the core losses will also become small anyway. So firstly we block the rotor, not allow it to rotate, locking it, and then we just reduce voltage, usually much low voltage, just 10%, 20%, 30%, not too high. And then we also can use a lower frequency to drive them if we can. If we cannot, we can still using the main frequency to drive them. So we try to record all the voltage and current and the power. So that's a standard way we can do that, because using oscilloscope, you can measure all of them, or using the the power meter, you can measure them. So once we have this three measurement, then our formulation will be quite straightforward. Firstly, we can convert everything into per phase value. If our measurement is total power, then like the 2 meter or other measurement method, we just need to convert them into per phase parameter. So the voltage we can divide by √3 become is per phase voltage, and the current is unchanged because they are started connected, and the power we divide by 3. So now again, the impedance. So as I mentioned before, we got resistance magnetizing, and then we got the R1, X1, and then X2 dash R2 dash. Yeah. We have this component. So we have this component in the equivalent circuitry, right? So this is the circuitry we now for the lot water test. Yeah. So from here, then we can, the power we measure in here, then divided by the current will give us the real component. You see, this real component are now more related to the winding because we don't need to consider the core losses. The core losses here at low voltage, they are quite small. So mainly this one will be the winding. And then we can get the X component from the impedance and also the real part. So now then we have the X component combination of these two X components, right? So the two inductance here, we don't know which one is which because they connect in series. In theory, we cannot separate that by simple log motor test. But we use the light transformer, we can assume them to be half and half. So that will be good enough. But it all depends on the motor design. Because from lemma design, the standard lemma design provides you with different kind of motor design method. If the motor is designed certain design method, like the design method BCDK, the parameter for that particular ratio can vary from 0.2 to 0.6. So you can use the table to estimate about how much portion here and how much portion here. But if you don't know, you can assume that 0.1. Because for most of calculation, we don't need to so strictly know exact ratio. So that gives us the total, and also you're able to estimate individual parameter. Then for the motor resistance as well, because we know the total from this formulation, then R1 we can measure it. So that means R2 we can also measure it. So that's quite straightforward. So from this log water test and water test, they are able to get most of the parameter. Okay, any question up to this point? You see the testing method are very similar to what we did for the industrial motor. So next section, we try to show you again about the three-phase configuration. Just now we did the star connection, but for the delta motor could be also quite popular connection. So now then the phase voltage and line voltage with primary correlation are all shown here. So it's time's up, right? You all take them. So go home to try to study more about correlation between line voltage. You can see that the line current going here split into these two. So they got a free relationship. But the phase voltage and the line voltage are the same because they're all parallelly connected. So that's how the correlation between them. Okay, again, so I stop here and then see you again on Wednesday. So I think on the first day, we'll start a new set of the lab, right? That will relate to induction motor and also brushless DC. I haven't touched the brushless DC motor yet. I will try to give you some kind of simple looks for you to start beforehand. Okay, again, see you again on Wednesday.